AI agents exhibit many of the same reliability challenges as distributed systems, with the added complexity of non deterministic decision making. As a result, designing reliable agents requires a different mindset than designing traditional software. There are many potential points of failure. Agents must first understand the user's intent from natural language. They then reason about possible solutions, create execution plans, dynamically select tools, and adapt their approach as new information becomes available. Along the way, they may also retrieve context from memory, maintain state across multiple steps, and coordinate with external systems. Each of these stages can introduce uncertainty. For example, model can misunderstand user's intent. Its reasoning could be flawed, or it could choose an incorrect tool. Agent's memory could be stale or incomplete, an external API could fail, or agent could create an invalid plan. All these are examples of failures that can happen in agentic workflow. What is important to realize is that overall reliability in an AI agent is a product of reliability of each of these components. As more steps are added, reliability decreases unless each stage is carefully controlled. And this is why reliability becomes harder as we move from traditional software to autonomous agents. Before we talk about reliable AI design, it is useful to understand the major ways AI agents can fail. While agent system can appear complex, most failures actually fall in one of the six categories. The first category is model errors, which originate from the model itself. Agent may hallucinate facts, make flawed assumptions, reason incorrectly, or generate answers that sound very confident but are wrong. Even with perfect data and tools, model can still make mistakes. The second category of errors is related to the context. Here, model may be functioning correctly, but it's working on wrong information. The agent may retrieve outdated or irrelevant context, miss critical context, or rely on stale memories. In many production systems, context problems are actually more common than model problems. The third category of errors is tool errors. Agent may select a wrong tool or make an unauthorized call to a tool. It may pass incorrect parameters, encounter API failures, or receive incomplete data from an external system. The fourth category is workflow or planning errors. The agent may create a wrong plan, skip important steps in the plan, or execute steps in a wrong sequence. It can get stuck in loops or conclude a task before the goal is actually achieved. The fifth category of errors fall under policy and safety errors. These errors occur when agent violates business rules, compliance requirements, security controls, or safety constraints. Examples include exposing sensitive information, accessing resources without authorization, or performing business actions that should have required approval, such as approving a large loan or refunding a large amount. And finally, there are human process errors. Not all failures originate from AI systems itself. Many occur because of the breakdowns in the surrounding process, such as incorrect inputs from the users, missed approvals, skipped validation steps, or poor handoff between people, agents, and business systems. Most agent failures that you will encounter in production can be traced back to one of these six buckets. Once you learn to classify the failures this way, designing a system with the right guardrails becomes much easier. The key takeaway here is that different failures require different solutions. A better model will not fix a missing retrieval problem. A better retrieval will not solve a policy violation, and a retry will not fix a flawed workflow. Therefore, to build reliable agents, you must identify the category of failure and then apply the appropriate control. Now that we have learned about different kinds of failures, the next question is, how do we solve them? Often teams assume that better model, more prompting, or more data will solve everything. In reality, different failures require different types of controls. For example, model errors are usually addressed through validation and verification. We do not simply trust the model's output, instead, we check whether the output is correct, complete, and aligned with the expectation. Verification is usually performed using either rule based checks or another large language model. Context errors are primarily a validation problem. We need to validate that agent retrieved the right information, the information is relevant, complete, and up to date. Tools error require a different mindset. Here, we need to enforce controls to constrain which actions agents can do and which they are not authorized to. We also need to take into consideration the unexpected errors which are beyond control, such as API failures or network timeouts. These can be controlled by incorporating recovery mechanisms to handle these failures gracefully when they occur. To avoid planning errors, we need to verify that plans that have been created are reasonable and complete. This can be done using rule based checks or large language model. And then we need to add recovery mechanisms that will allow agents to detect and subsequently correct the mistakes before they cascade. Policy and safety errors require strong enforcement and governance. These errors require focused prevention rather than detection. Violations should not happen in the first place. And finally, the human process errors require governance and verification. These issues require approval workflows, an audit trail of human actions, separation of duties, and validation steps that reduce the risk of mistakes that are introduced by people. The key idea here is that reliability is not one thing, it is a collection of controls that are applied to different failure modes. Before choosing a technical solution, we must first understand what type of failure we are trying to prevent. This gives us our solution mindset, which is validate what can go wrong, verify what must be correct, ensure what must be constrained, govern what requires accountability, and recover when failures inevitably occur. An important point that I want to make about verification using large language model is that verification itself has a cost. Every additional check can add latency and expense in agentic workflow, and this becomes a trade-off in most agentic designs. In production systems, we don't verify everything equally. We use lightweight deterministic checks whenever possible and reserve expensive large language model based verification for high risk or uncertain situations. Now that we know the different categories of errors and the solution mindset, let us talk about how we can design resilient AI agents. Resilience can be defined as the ability of an AI agent to continue working on its goals even when failures occur. It is built around four capabilities: prevent, recover, observe, and learn. First, we should try to prevent failures through validation, guardrails, and safety controls. This is what we will learn in this episode and the next episode. When failures inevitably occur, we recover using mechanisms such as retries, fallbacks, and escalation to human. We then observe the system through monitoring and human overview so that we can detect issues quickly. And next, we adapt and learn by analyzing failure and continuously improving models, policies, and workflows. Together, these four form the integrated resilience loop where prevention, recovery, observation, and learning reinforce each other over time. In this episode, we will mainly focus on the prevention techniques for common failures with AI agents. For failure prevention, there are three broad concepts: policies, validation, and guardrails. These terms are often used interchangeably, but they serve very different purposes. Policies define rules. These rules come from business requirements, organizational standards, and security and compliance regulations. Validation checks for correctness. It asks the question: is this information correct, complete, and consistent? And guardrails enforce policies. They answer the question: is this action allowed? Based on policies and validation results, guardrails actively constrain agents' access, its action, and its response. For example, for a travel booking agent, the policy states that flights over $2,000 require manager approval. Validation checks that ticket costs $2,500 and therefore guardrails block the booking until required approval is received. So, a useful way to remember this is policies define the rules, validation checks the facts, and guardrails enforce the outcome. Now, let us look at various categories of validation controls that can be applied throughout the agent lifecycle. The first category is input validation, which focuses on validating what comes into the system. Here, we verify that request is legitimate, complete, and safe to process. Common checks include intent classification, prompt injection detection, PII detection, and schema validation. For example, before a travel booking agent proceeds, it may verify that all required passenger details are present and correctly formatted. The second category is output validation. Even if the agent executes correctly, we still need to verify that final response is safe, relevant, and properly structured. This includes check for sensitive information, relevance with user's intent, safety and policy compliance, and response schema validation. Think of this as the final quality control step before the information reaches the user or another system. And the third category is state validation, which focuses on agents' internal state. Agent systems are often long running and multi step processes, so we need to ensure that they remain in a valid state throughout the execution. For example, if agent is booking a flight, before proceeding to payment, it may validate that traveler details are present, the selected itinerary still exists, and the workflow has not skipped a required approval step. State validation checks for context errors and workflow errors. Validation alone cannot stop anything. Once a problem is detected, we still need a mechanism that decides what the agent is allowed to do next. And this is where guardrails come in. Guardrails can be applied throughout the execution lifecycle. At the top, you see the behavioral guardrails. These are broad policies, instructions, and constraints that apply to the entire lifecycle. They define what an agent should and should not do, regardless of the current step. For example, a healthcare assistant may have a guardrail to provide general information but never give any diagnosis or prescription. This applies regardless of what step the agent execution is on. As the agent moves through the execution, we apply specialized guardrails at different stages. We apply input guardrails at the entry point, state guardrails during context retrieval and workflow execution, reasoning guardrails for plan and intermediate reasoning, tools guardrails to control how external tools are called, and output guardrails before any output is sent to the end user. Let us look at some common controls that are applied at each stage. Input guardrails validate input for intent, detect prompt injections, and identify sensitive information. And based on these checks, guardrail may either allow the request to proceed, require additional validation, redact sensitive content before sending it to the model, or block the request entirely. State guardrails ensure that retrieved context from the data sources is complete and relevant to task. Agent's own memory remains consistent and up to date, and the state checkpoints with workflow progress are valid. Reasoning guardrails control agent's thinking process. They check whether goals and plans are in alignment with user's intent, they are complete, and they also check if agent is getting stuck in loop or repetitive reasoning. Based on these checks, guardrails may allow the execution to continue, trigger replanning, request additional information, or stop the workflow. Before the agent interacts with external systems and tools, we verify that tools are approved for use and agent has authorization to use them. We also check that the parameters being sent to tools are safe and valid. Based on these checks, guardrails may allow the tool call, modify or constrain the parameters, require approval to use that tool, or block the action entirely. This is often the final control point before agent can affect external systems, making this one of the most important layers for preventing costly or unauthorized actions. And finally, we have the output guardrails, which ensure that we do not pass any sensitive information, we comply with the policies, and response is accurate, safe, and relevant to the user's query. Now let us see these controls in a typical agent request flow. The first checkpoint is input validation, and here we authenticate and authorize the user. We validate the request against a schema if applicable. We check for prompt injection attempts and enforce any policies on the input that we can process. We also look for request limits at this stage. If the request fails these checks, it is blocked immediately. Once the request passes the validation, it enters agent's execution loop, and here the agent plans, acts, and observes. During the planning phase, we break down the goal so that we can ensure proper reasoning. We apply business policies and we self critique the plan after we have created it. This is typically done using another large language model. When we invoke the tool, we ensure that model is allowed to invoke the tool. It is sending the right parameters, and if there are errors, they can be handled gracefully. And once we get the response in the observe phase, we validate the tool output using a schema or any policy constraints. We detect anomalies, and if there is a need to trigger recovery, we trigger that. The memory is managed and governed separately throughout the process with controls around access, privacy, retention of memory, encryption, approvals, etc. There is a separate session on memory management that you should watch if you want to learn more about this. For actions that may have significant business impact, we perform a risk assessment. If the confidence is low or potential impact is high, the workflow can be escalated to human for a review. This ensures that critical decisions receive additional oversight. And before any real world action occurs outside of the agent execution loop, such as approval of a refund, issuing a loan, or modifying a customer account, we perform external action validation. And as I shared earlier in the previous screen, this is one of the most important checkpoints because once an action is executed, it may be difficult or impossible to undo. We verify the calculations, check policies, and scan for privacy and compliance issues before proceeding. And after these checks are passed, we execute the external actions. Even then, we monitor for anomalies and use retries or recovery mechanisms if failure occurs. This is similar to how we do it in the act phase of the agent execution loop. And finally, before the response is delivered to the end user, we perform the final response check. We validate the output for safety, we scan for sensitive information, verify relevance with user's goal, and look for potential hallucination. So, the key takeaway here is that prevention is not a single guardrail at the beginning of the workflow or end of the workflow. Reliable agents apply validation, policies, guardrails at every major decision points from the initial request all the way to the final response. In this episode, we learned how policies, validations, and guardrails can be applied throughout the AI agent's execution lifecycle to prevent failures and improve reliability of the agent. In the next episode, we will dive into the technical solutions that can be used to implement these controls in a production system.